Here are solutions to homework set number 11 for ECE 461-661 control systems. In this homework set, we're looking at designing digital PID controllers. So the first problem is, given an analog system, come up with an I compensator that's discrete. So this is in the S-plane, K is in the Z-plane. There's a couple ways to design this. One approach is convert G of S to the Z-plane, then everything's in the Z-plane, draw the root locus in the Z-plane, and find the spot that has 20% overshoot. At any point in the root locus, G times K is minus 1. Find K, and you have your design. That's one approach. I'm going to use a slightly different approach. What I don't like about the first approach is I've got to convert G of S to G of Z. That's kind of painful, and it's a little bit inaccurate. Typically when you do that, I need to have like 1.5, 2.5 zeros at the origin, and I can't do half a zero. So no matter what you do, you're wrong, either round up or round down. Since the model's wrong, the result is wrong. A more accurate way of doing it is use numerical methods. What I want is any point on the root locus, G times K is minus 1. My open loop system is G of S times the zero order hold times K of Z. So this is a mixed plane analysis. As long as I can analyze it, I can still work just fine. Well, G of S, I know, that's given. The zero order hold, a good model of it is just a half sample delay. Then K of Z is just K of Z. If I know S, I know what Z is. Z is e to the st. So what I'm going to do is, in the S-plane, I'm going to search along my damping line. That's my minus 1 plus J2. That's 20% overshoot. Search along that line until the angles add up to 180 degrees. Once I find that spot, that's my design point. Now there is a root locus plot. I may not know what it is, but I don't really care. I just want to find this one point. So doing that, I search along the line till the angles add up to 180, and it turns out the point where the angles add up is at minus 1.13 plus J2.27 in the S-plane. In the Z-plane, that spot is 0.869 plus J.201. So here's what I use for S, here's what I use for Z. Multiply it all out, and the angle's 180. Gain is wrong. Pick K to make the gain 1, and K is 0.4551, so there's K of Z. The last part of problem 1 is now check your answer. What I could do is in the Z-plane, do G times K over 1 plus G times K. That's all in the Z-plane. MATLAB doesn't like mixed plane. Then take the step response. A better approach is if you can find Vissim or Simulink. Simulink is MATLAB's version. Vissim is another version. I can actually do a mixed plane analysis. Here is K of Z. That's in discrete time. You can tell by its output having stair steps. Here's your G of S. That's continuous time. Its output is smooth. Close the feedback loop, and what I should get is 20% overshoot, and sure enough, I do. That's kind of what I like about this approach. It gives you the right answer. And if you don't mind doing numerical methods, it's actually pretty easy. So that's problem number 1. Problem 2 says, let's design a PI compensator in the Z-plane. Well, for a PI compensator, it's in this form. I've got a 0 anywhere I want to put it, the pole at plus 1, that makes it a type 1 system, and a gain K. The 0 I picked to cancel the slowest stable pole, so I picked the 0 to cancel this pole. This is the pole in the S-plane. In the Z-plane, the pole is at e to the st, or 0.7681. So here's the form of K of Z. Now it's just like problem number 1. I want to search where along my damping line, so here's my damping line, where along this line do the angles add up to 180 degrees. I do a search, and I find out that the solution is right here at minus 5.22 plus J10.44. That's in the S-plane. Z is e to the st, 0.298 plus J.512. As a check, plug in those points, I get 180 degrees. Gain is wrong. Pick K to make the gain 1, so there's K of Z. To check my answer, again I'm going to use Vissim, just change my K of Z I now have a much quicker system. The settling time is now about 1 second. 20% overshoot. No error for step input. The no error is due to this pole. That's a type 1 system. That's a lead compensator. PID compensator. What PID means is I have a proportional term, integral, and delay. So here's my delay. There's the integrator. If I have 2 poles, I can add 2 zeros. Put the zeros anywhere I want. This one cancels the pole at minus 2.6. That cancels the pole at minus 30. Cancel the 2 slowest poles. So convert those poles to the z-plane as e to the st. There's 0.76, 0.04. What this tells you is the d term doesn't really do much. That basically cancels. Essentially, I've got a z minus 0.04 over z. That's almost pole zero cancellation, so this doesn't really do much for you. What that's telling you is that I need a higher sampling rate to move this pole away from the origin. But going with it, here's the form of k of z. Search until the angles add up to 180, and now I get the answer minus 5.58 plus j11.1. If you kind of notice, that's not a lot different than the last problem. Last problem I was at minus 5.22. This one is a little bit better, not much better. Instead of 5.22, it's 5.58. So basically, I didn't really do much. At that point, angles add up to 180. Pick k to make the gain 1. K is 1 over 0.15, 6.4. So there's k of z. Checking the step response, here's my new improved k of z. It is a slightly faster system. Now the settling time is about 0.8 seconds. 20% overshoot. No error for step input. That looks like a correct design. Next problem. Problem 4 is come up with a compensator to meet these design specs. So basically I can add poles and zeros wherever I want. As long as they meet these specs, it's a valid solution. And there's actually an infinite number of solutions. One way to come up with a solution is translate this to the S-plane and Z-plane. I want 20% overshoot. Actually, 2% settling time of 1 second. Says the real part's at minus 4. 20% overshoot says the complex part is J8. So here's where I want to put the closed loop pole in the S-plane. Z is e to the st. Here's where I want to put the closed loop pole in the Z-plane. I need something to adjust. So what I'm going to do is add 2 zeros and 2 poles. The first zero cancels the pole at 0.26. The second cancels the pole at minus 30. Add a pole at plus 1 to make it a type 1 system. Add the second pole wherever it takes to place the closed loop pole at minus 4 plus J8 in the S-plane. So here's the form of G of S times zero order hold times K of Z. Now let's analyze what I know. I don't know K, I don't know A. Analyze everything else, and I get minus 115 degrees. Should be minus 180. So the pole that I ignored, that Z minus A, that must contribute 64 degrees. So doing some trig, here's my design point in the Z-plane. It is 0.46 plus J 0.48, 0.46 plus J 0.48. Here's where I added the pole, that's A. This angle is 64 degrees. So doing some trig, that point is the complex part of the pole, correction, the real part of the pole, 0.46, pulled left, minus the complex part over the tangent of the angle gives you 0.23. So checking, here's what I know right now. Plug that in at my design point, minus 4 plus J8, I get 180 degrees. So this is correct. Gain is wrong. Pick K to make the gain 1, and you get 4.17. So here's K of Z. And if you plot the step response, it's what I expected. 20% overshoot, settling time is 1 second, and no error for step input. Problem number 5. Suppose somebody comes along and says, you know, I don't want a 0.1 second sampling rate, I want a 0.05 second sampling rate. Modify your design for a 50 millisecond sampling rate. Well, when you change the sampling rate, that completely changes G of Z, that completely changes K of Z, it's basically a complete redesign. So if you're a control engineer, you really grumble at the person that changed the sampling rate. That means you take your old design, scrap it, start over. So it'll be similar to before. I've got 2 zeros, 2 poles. This cancels the pole at minus 2.6. This cancels the pole at minus 30. The zeros change in the z-plane because the sampling rate changed. Z is e to the st. Change t, you change z. So here's the form of the solution. I want to find out what is A to make the angles add up to 180. So analyze everything that I know. Don't know K, don't know this term. Analyze everything else at my design point. I get minus 123 degrees. I'm off by 56. So again, doing some trig. Here's my design point in the z-plane. It is 0.75 plus j.31. So this angle is 56 degrees. So A is 0.75, the real part, minus, go left, the complex part, over the angle gives you 0.54. Checking your answer. Angle should add up to 180. They do. Pick K to make the gain 1, and K is 3.14, so there's K of Z. And now when I check the step response, again 20% overshoot, settling time is 1 second, no error per step input. That's another perfectly valid solution. And there's actually an infinite number of solutions that work. This is one of them. So that is homework set number 11 for ECE 461.